Here is the source follower that we obtained by trying to construct a voltage controlled voltage source of gain 1 around a single MOS transistor using negative feedback, and then adding an appropriate biasing scheme to it. Okay, we have done the analysis as well. We know the input resistance and the output resistance and the expression for the gain. Now there are a few small details remaining. One is the effect of channel length modulation, that is non-zero output conductance of the transistor, and then also to find the constraints on C1 and C2. Okay, so let's take these things one by one. The small signal picture is this, and I will assume that the capacitors act like short circuits at the signal frequency. C2 would have been there. This is VGS and the current is GM VGS. Now this of course assumes that there is no output conductance for the transistor, but if there is an output conductance, then it would be connected between the drain and source terminals of the MOS transistor. That's where GDS would be. Okay, and the effect of this is very easy to analyze. Okay, you can see that this GDS appears across RL. Okay, so RDS appears across RL. So this means that in all the expressions, wherever you have RL, it should be changed to RL parallel RDS. Okay, this is in the expression for gain. We have GMRL by 1 plus GMRL for the original circuit with RDS equals infinity or GDS equals 0, and this should be changed to GM times RL parallel RDS divided by 1 plus GM times RL parallel RDS. Okay, or another way of writing it is GM by GM plus GL plus GDS. Okay, and the condition for nearly unity gain is that GM times RL parallel RDS to be much more than 1, or GM to be much more than GL plus GDS. Okay, and it doesn't make any difference to the input resistance. In this case I didn't show R1 parallel R2, but whether it is there or not, the resistance looking in here is not affected by RL in this particular case. In general it can be in a circuit, but in this case it's not. Okay, so Rn is not affected, the gain is affected. The gain will reduce a little because essentially you have an extra load. Instead of RL you have RL parallel RDS. And as far as the output resistance is concerned, let me copy over the circuit. We compute the output resistance looking that way. Okay, and Vi is set to 0. That means this becomes a short circuit, and this is very easy to compute. First of all, you can notice that this GDS simply appears between the output terminal and ground. So whatever output conductance we had calculated earlier, which was equal to GM, now we will have an additional GDS, but we can also evaluate it and see. If I apply V test here, the gate voltage is at 0 because this is 0 and no current flows into the gate, and the source voltage is at V test, so VGS equals minus V test. So this current source here is minus GM V test, and the total current going in here is the current in this going upwards plus the current in that going upwards, and the current in this going upwards is V test times GDS. So this total current will be minus GM V test is simply GM times V test going upwards. So this total current is GM plus GDS times V test. Okay. So the output conductance is the current divided by voltage. And obviously this gives you Gm plus GDS, or if you want the output resistance, it is 1 over Gm plus GDS. Now Gm is likely to be much more than GDS when you bias the transistor in saturation region. Okay, so this doesn't change the output resistance by much, it reduces it only by a little bit. Okay, now I'll draw the small signal equivalent including the capacitors so that you can find the constraints on them. Here is the input voltage Rs C1, and we'll have R1 parallel R2 between the gate terminal and ground. The drain is connected to ground, and this is connected through a capacitor C2 to RL. Okay, this is Gm times VGS, where VGS appears here. Now the input side of this is very familiar, right? If you set Vi to 0, what is the resistance that appears across C1? We have calculated this many times. So the resistance across C1, this is basically Rs plus R1 parallel R2. Okay, so the constraint on C1 is that it should be much greater than 1 by the signal frequency omega in radians per second times Rs plus R1 parallel R2. Okay, as usual, while calculating C1, you short circuit C2, but I mean in this case it doesn't matter because the value of C2 doesn't affect the value of C1 anyhow. The circuit is truly decoupled. Okay, now as far as calculating C2 is concerned, we set the input to 0, and because the input is 0 and no current flows into the gate, you can easily work out that this voltage is at 0. Okay, this is true whether you have a C1 that is very large or not. Okay, so this will be at 0. Now you have to find the resistance that appears across C2. Okay, how do you do that? There are a couple of ways of doing it. I'll choose the easy way. You can of course connect a voltage source V test, and it has to be connected, remember, between this terminal and that terminal, and calculate the current flowing I test and take the ratio. Okay, now we have already done part of the calculation, right? Because this picture, it looks like this. We have C2 and RL connected to ground, and it's going into the output of this source follower, which is also connected to ground, and this is the output terminal. Now we know that when the input is set to 0, looking back in here, what do we see? We see the output resistance of the source follower. In fact, we use this method also for the common source amplifier with drain feedback, right? So you see the output resistance of the source follower, and if I write that here, show it as the resistance between that point and ground, and this is what we'll have. So what is the resistance that appears across C2? You can clearly see that it is RL plus the output resistance of the source follower. Okay, and the output resistance of the source follower is 1 by Gm if you neglect GDS, or 1 over Gm plus GDS. Just for simplicity, I'll use this expression, but you can also use this. It's anyway not going to be much different from that one. Okay, so this is equal to RL plus 1 by Gm. Okay, so what is the constraint on C2? The reactance of C2 must be much smaller than the resistance that appears across it. So C2 has to be much more than 1 over the signal frequency omega in radians per second times RL plus 1 by Gm. And for a source follower to behave like a source follower, like a unity gain buffer, anyway you need GMRL to be much more than 1. So this means that RL is much more greater than 1 by GM. Okay. So this constraint approximately is that it's 1 over omega times RL. Okay. So again, quite easy to compute, and it's computed in a way that's similar to what we have done many times before. And just for practice, I would encourage you to actually connect the test source between these two terminals and find the current. That will give you some extra practice in circuit analysis, and of course you should get exactly the same answer that I got. Okay. So now we have everything that we want to know. If we want to design a source follower, the gain of that is GMRL by 1 plus GMRL, or if you want to include GDS, GM times RL parallel RDS, 1 plus GM times RL parallel RDS. By the way, notice that I use the conductance form or the resistance form depending on whichever is convenient. You should also get used to it because that's quite commonly done in circuits. And the input resistance is really due to the biasing resistances. The output resistance is 1 by GM or 1 over GM plus GDS, and the capacitors have these constraints. That's the constraint for C1, where RS is the resistance of the driving source, and C2 has to be much more than 1 over RL plus 1 by GM times the signal frequency omega. Okay. So with this you should be able to design a useful source follower given the value of RS and RL. Okay, given the value of RL, you choose GM such that GMRL is much more than 1. That is necessary. And given the value of RS, you choose R1 and R2 such that the combination R1 parallel R2 is much greater than RS. Okay, so that way there is no attenuation and you get a nice unity gain buffer. Okay.